We're now going to proceed to work out a couple of examples illustrating how you should find the lim sup and lim env of a given sequence. So we're going to first look at sequence n minus 1 over n plus 1. And at the first step, I want to find lim sup of that sequence. So the way you do it, if you remember the definition that we wrote down last time, what you need to do is to find the supremum of the terms of your sequence starting from the kth element, which means starting from the first element, second, third, fourth, etc. This will produce a new sequence vk, and then you'll take a limit of that sequence vk as k goes to infinity. But first we need to find the supremum. And in this case, it would be easier to actually divide the numerator by the denominator. I can do that in a simple way by adding 1, writing minus 1 as 1 minus 2. And then we can split this fraction into a difference of 2. One is n plus 1 over n plus 1, which is 1. And the remainder is minus 2 over n plus 1. Then the circle term here is always negative because of a minus sign in front of it. And also the expression that I circled here, 2 over n plus 1, will be going to 0 as n goes to infinity. So 2 over n plus 1 minus 2 over n plus 1 is negative, but at the same time, it is arbitrarily small as n goes to infinity. So then you should convince yourself pretty easily that that means that the supremum overall n greater or equal than k is actually going to be 1, right? Because I'm subtracting from 1 numbers that are getting infinitesimally small. Okay, and so then my sequence vk is sort of a trivial sequence of constants, because it doesn't matter what k is, the answer that I'm always getting for vk is 1. And so then the limit of that sequence, the sequence of ones, must be 1. So lim sup of n minus 1 over n plus 1 is a limit of vk, right? Which is the limit of the suprema that we found. And those suprema are all 1, so limit of ones is 1. And so this is my lim sup. In this case, it's 1. We can try to do a similar thing for lim env. What you need to do for lim env, you need to find the infimum now when n is greater or equal than k of your sequence, right? So starting from a certain index k, you find the infimum of the remaining element in a tail of a sequence. Do the same thing, do the long division. So you have to take an infimum of this expression. And what is the infimum? So in this case, 2 over n plus 1, again, it is a sequence which is which goes to 0. And not only it goes to 0, but if I look at just 2 over n plus 1 by itself, it goes to 0 monotonically. So 2 over n plus 1 is a decreasing sequence. So minus 2 over n plus 1 will be an increasing sequence. And therefore, and 1 does not really affect adding 1 to minus 2 over n plus 1, really does not affect the monotonicity. So 1 minus 2 over n plus 1 is still an increasing sequence. And if it is an increasing sequence, then its infimum must be also its minimum, the first element of the sequence. And since in this case I'm starting from n equal to k, then the infimum must be 1 minus 2 over k plus 1, as I indicated here. All right, and then lim env is a limit of uk's. So lim env for that regional sequence is a limit of these uk's that I found. UK's are 1 minus 2 over k plus 1, so I just need to take this limit, and the limit is equal to 1. So if we use this computation to motivate our discussion from last time. In this case, what I see is that both lim sup and lim env are equal to 1. So that means that as n goes to infinity, my sequence can only get as high as 1 and as low as 1. So that means that the window of oscillations in this case, as n goes to infinity, reduces to an interval from 1 to 1, which is just 1. There is nothing else in this interval. So that means that in a limit, the sequence must converge to 1. And we know that, in fact, without taking lim sups and lim env, if I just take a limit of n minus 1 over n plus 1, just by using properties of limits, I should be able to easily show that the limit is 1. This is similar to the examples that we have already done. All right, another question of a similar type. So I have a different sequence. Now it is minus 2 to the power n. And again, I want to find lim sup and lim env. And again, if I want to figure out lim sup, I need to take a supremum of minus 2 to the n, when n is greater or equal than k. What is the supremum of that? So there is a minus sign here. Minus 2 to the n, I can basically think of as minus 1 to the n times 2 to the n. Minus 1 to the n is oscillating between minus 1 and 1. And 2 to the n is getting arbitrarily big because I get 2, 2 squared, 2 cubed, 2 to the 4th, right? Each next term is twice as big as the previous one in size. And so that means that the sequence that I'm seeing is going to oscillate from positive to negative, but at the same time it will increase in size. And increase in size without any bound. So then if I'm taking supremum, that's the least upper bound, then negative numbers are of no interest to me. I just follow the positive numbers. And the positive part of my oscillations. But again, because the amplitude of oscillations goes to infinity, that means that the supremum is infinity for any k. And likewise, well, actually before likewise. And so then if you take lim sup of minus 2 to the power n, you need to take a limit of these vk's that we found. All vk's are infinity, so formally the limit of infinity is infinity. Very similar thing for the lim env, except that now I have to take the infimum of the same terms when n is greater or equal than k. Once again, the sequence minus 2 to the n is going to be oscillating up and down while increasing in size. So that means that this sequence is unbounded from below, and therefore its infimum is minus infinity. And then lim env should be the limit of these uk's. Limit of minus infinities must be minus infinity. So in this case, lim sup is plus infinity, lim env is minus infinity. What does it mean? It means that my sequence is oscillating in a larger and larger window. So as n goes to infinity, it will keep jumping between plus and minus infinity. Okay, so those are a couple of examples, and now we're going to prove a few theorems which relate, eventually relate lim env, lim sup, and lim, and just a regular limit. But to get there, I need to prove a couple of relatively easy results. So the result number one, let's suppose I have two sequences. Sequence number one, Sn converges to S. Second sequence Tn converges to T. And let's suppose that I know that elements of Sn are element-wise larger than elements of Tn. So S1 is bigger than T1, S2 is bigger than T2, and etc. And then the obvious conclusion from that is that that means that the limit of S must be greater or equal to the limit of T. Let's try to prove this fact. And I'm going to try to prove it by a contradiction. So let's suppose that S actually is not bigger or equivalent to T, but that it is less than T. So if S is less than T, then T minus S must be a positive number. So if I take T minus S divided by 2, that's a positive number. I can denote it by epsilon, or I can choose epsilon, which is equal to T minus S over 2. Fine. All right, so now let's think about S minus T. What is S minus T? It's S, limit of Sn minus T, limit of Tn. By the properties of limits, the difference of two limits is the limit of a difference. And then if the limit of a difference, limit of Sn minus Tn, is equal to S minus T, then I can write the definition of a limit. And definition of a limit says then that Sn minus Tn, which is a sequence that I'm taking, minus its limit, absolute value of that, can be made less than any initially prescribed epsilon. I chose this epsilon, so there exists an N and R such that this is going to be true, right? It should be true for any epsilon, but I'm interested in looking at T minus S over 2. And that is going to be true as long as N is bigger than capital N. That does exist in this case. Okay, I will try to rewrite this expression without using the absolute value sign. So that means that Sn minus Tn minus S minus T is bigger than minus epsilon and less than epsilon, as long as N is bigger than capital N. I am going to look only at the second half of this inequality, the one that I underlined here. What can I say about it? Well, I can take S minus T and add it to both sides. Then Sn minus Tn would be less than S minus T, which goes to the right, plus T minus S over 2. But remember also that we assume that Sn is bigger or equal than Tn for all n, so that means that Sn minus Tn also is a number greater or equal than 0, right? Because Sn is greater or equal than Tn. And then S minus T plus T minus S over 2 can be simplified into S minus T divided by 2. And what is S minus T? S minus T, by my assumption about S and T, S is less than T, so S minus T must be less than 0. So this would be less than 0. But then what have I got? I got that 0 is strictly less than 0. That's impossible, right? Because 0 is equal to 0. So this is a contradiction, and therefore my assumption that S is less than T is incorrect, and the opposite must be true, which is S is greater or equal than T. And then using this, I can immediately see the following fact, that lim sup of Sn, as n goes to infinity, the limit superior is going to be strictly, not strictly, but greater or equal than the limit inferior lim inf of Sn. Now, why would this be true? By definition, for any k, we introduced uk, which is an infimum of Sn and greater or equal than k. If I replace infimum by the supremum, that's certainly, or the same set, certainly supremum is going to be greater or equal, and supremum was denoted by vk. And so now uk is less or equal than vk for all k, right? The less equal sign comes from here. And so then if I'm taking lim nth of Sn, that's the same thing as the limit of uk. Limit of uk is less or equal than the limit of vk, but the limit of vk is lim sup. And so once again, following this chain of inequalities, then lim nth must be less or equal than lim sup. Okay, so with that, in the next lecture, I'm going to prove an important theorem which relates, as I said, lim sup, lim nth, and the limit of a given sequence.